Today we're going to talk about redox reactions and how we predict the products of these types of reactions. Now remember, redox reactions involve the gain and loss of electrons. It's going to become really important that we recognize some common substances that are being reduced and some common substances that are going to get oxidized. We need to know our common ion charges. Those are just some of the things that we'll need to know in order to be able to do these types of reactions. Now, looking at this table right here, it's just giving you some ideas of some things that you're going to see over and over again. If you start out with permanganate in an acidic solution, it is going to end up forming Mn2+. It always does. In basic solution, it often forms MnO2 when it's in basic solution, but in an acidic solution, Mn2+. Now the dichromate ion, if it's an acidic solution, will end up forming Cr3+ on the other side after it reacts. So there's just no way to know how to do this unless you memorize it. So you really have to memorize it. We get HNO3 concentrated, forming toxic NO2. You'll see that happening today. Dilute nitric acid forming non-toxic, no, it's not toxic, nitrogen monoxide. And hot concentrated sulfuric acid will reduce down to SO2. Metallic ions will often go to metallus ions. That's why we have to know our common ion charges, Fe3+ down to Fe2+, Cu2+ down to Cu+. Sometimes they'll go all the way down to the free metal when they're being reduced. Free halogens will often get reduced on down to their negative ion state like it shows here. So those are some common things that happen. And they'll go in the opposite way. Halide ions will be oxidized to form free halogens. So halide ions, like we showed up here, the F-, Cl-, Br-, and I-, will get oxidized back up to their zero free state as diatomic elements. You can refer to this chart and see some of the things that will happen. The free metals up to the metal us ions, that lowest ionization energy. So for or ionization energy, that lowest common oxidation state. So copper, for instance, it might go up to copper plus. Fe might go up to Fe2+, etc. And our us ions, like Cu+, might get oxidized on up to Cu2+. And our Fe2+ might get oxidized on up to the ic form, Fe3+, the ferric ion. So those are some things you might see. Now I know that was a lot at once, but I just wanted to show you some things that you might see here at the beginning. Now when an AP equation mentions an acidic or basic solution, it says it's probably redox, but I've never seen it be anything else. Always add H+ and H2O to reactions that are acidified. So the very first thing I do, if something says acidified, I don't do anything else before I do this, because this is one of my Achilles heels. I'll forget the H+ and the H2O if I'm not careful. So the H+ is a reactant, the H2O is a product. Another thing that I always do, okay, this is something that we're going to have to get used to. Let's say we've got 10,2 chloride here. Remember, that means 10 is a +2, and since chloride's a -1, it's going to be SnCl2, and we're adding it to potassium permanganate. So potassium with the permanganate. Okay, I wrote it up here because I want you to get used to seeing what's going to drop out before you even try to do a redox reaction, because if you start trying to include the spectator ions, it's going to get so confusing so fast I can't even begin to tell you. So the first thing we want to do, and since we know this is going to be redox because it had that nice acidified in there, Think about what normally drops out when we split these. If we split these, what do we see dropping out over and over again? Chloride, potassium. Go ahead and do that before you ever start the reaction, and it will save you so much heartache in the end if you'll do that. So the way I truly want to start this reaction is by saying that SN2 plus is being reacted with MnO4 minus. Please don't forget the H plus here and the H2O here. Now, what we have to decide now is what's going to happen to these. And that's when it's very important to go back to our list up here and see what happens if we've got something that will occur in the redox reaction to one of these species. And MnO4 is a classic, guys. It says right here that MnO4 in acidic solution is going to react to form Mn2 plus. Just go ahead and write it down. You'll see it so much, you'll get to the point where you memorize it. So Mn2 plus. And so we started out with Mn7 plus. If you remember, manganese is the 7 plus in permanganate. We ended up with a 2 plus for manganese over on the right-hand side. Does it make sense to you that that was a reduction, that manganese went down in charge? Now, it's vitally important now that you remember, if something goes down in charge or oxidation state, something else has to go up in oxidation state. So our tin over here must go up in oxidation state. Think about what that would be. If tin goes up in oxidation state, remember, stay in the plumber. The higher oxidation state for tin is tin 4 plus. So that's what's going to happen over here. Since manganese went down, tin must go up. We have to know that tin is a 2,4, stay in the plumber, SN4 plus. Tin and lead both have 2 plus and 4 plus oxidation states. The beautiful part of redox reactions for right now is that I'm not going to make you balance them right now. I think it's hard enough for us to get used to doing this with just figuring out what's being formed without having to figure out how to balance it. So we're going to leave it in this unbalanced form for now. We'll get to the point where we're balancing them, but not now. Okay, so the next one. We're just going to do this every time we see a redox reaction. We've got potassium iodide. So I'm going to write them up here right now and see what I can drop out, because I see this nice little word right here, acidified, and I know it's going to be a redox reaction. I'm reacting that with potassium dichromate, Cr2O7. And I think about these splitting and what would drop out immediately. First of all, it should be fairly obvious that this is not going to be a double replacement reaction, because if we flip-flop those first elements, we would end up with the same thing we started with. So it does end up being redox. That acidified again is what tells us potassium is going to drop out over and over again, over and over again. So much better for us if we simply write down I minus and Cr2O7 2 minus first. Now, it's acidified. Again, I'm not doing what I said I should do, and that's write down the H plus and the H2O before I even get started. But so we've got this much going, and now we look back into our table and we find something that we see that happens all the time in reactions like this. And we go back up to the top and we see that Cr2O7 in acidic solution always forms that Cr3 plus. So let's go back down here and fix that. We know that it goes to Cr3 plus. So now we know one thing that happened, and think about it. We went from chromium. If you find the charge for chromium in here, it ends up being a +6. It's the same in chromate and dichromate. And it's going down to a +3. So this is going down in oxidation state. What does that mean about iodine? It has to go up in oxidation state, get higher in oxidation state. Well, where do those negative ions go to? Look back up in our chart, although I'm hoping you can figure out that if we have a negative ion, those halide ions, they go up to the free halogens. What do I mean by the free halogen? Well, iodide is going to go all the way up to iodine. And remember, iodine is diatomic, so it's going to go all the way up to I2. Don't put those charges in that we found just for deciding what was being oxidized and reduced and what our products were. So we do not have to balance it. We just have to come up with the substances right now. So that's the equation that I want you to write for this particular redox reaction. Now, I do want to show you a couple of ones that happen all the time, and this is with copper and nitric acid. Copper reacts with concentrated nitric acid much differently than it reacts with dilute nitric acid. If you have concentrated nitric acid, copper is going to react with that nitric acid. And what's going to happen is that we're going to form that copper compound, or we'll show it as a Cu2 plus. It's going to form Cu2 plus, it's going to oxidize, and since it's concentrated, we get that nasty, if you remember our rule up there, that concentrated NO3 minus ends up forming, as we see up here, the toxic NO2. So now I'm scrolling up and down quite a bit here, but I want you to pay attention to that table. And then in order to explain that we've got hydrogen, we better put some water here so we show that we have not destroyed some hydrogen somehow. We do not have to balance it, so we can leave it like that. The difference in the solution, if it's dilute nitric acid, we'll get the same startup. The difference is in the type of gas that's formed in the end. And the type of gas that's formed in the end is going to be the no, it's not toxic nitrogen monoxide along with the water. This one's easy to spot. It's reddish, brownish color, and it's really nasty smelling. This one's pretty much odorless. You don't even notice really that it's being produced. So there's a difference when you're dealing with concentrated nitric versus dilute nitric and copper.